Good morning, team. We are off on a new topic in a new direction today. We are trying to probe into this thing called an atom and try to figure out what's going on with these electrons. We're pretty good with protons and neutrons, right? We know they're in the nucleus, right? We know protons give us the identity of the atom. We know neutrons can give us isotopes, all that fun stuff, and they keep that nucleus together. But electrons we've been avoiding. We just said electrons are somehow moving outside the nucleus, and we kind of left it at that. All right, it's time to figure out what's going on with these, but it's a little harder than you think because trying to probe into an atom to go, oh, what's the structure look like, is easier said than done. It's not like you're in biology or something and you take a cell and you look under a microscope and you can slice it open and look at the stuff inside there. I'm not a biologist, so endoplasmic reticulum, mitochondria. You can see that through a microscope. You can't even see an atom through a microscope. It's too tiny, right? So we don't, at least today, we don't necessarily have the physical ability to directly probe into an atom. I mean, we can probe and see the presence of an atom. So if you want to look up a scanning tunneling microscope or something like that, we can see the presence of atoms. You can see images of them, but not inside. We can't cut it open and dig around and go, look, there's a neutron, look, there's an electron. So we need an indirect way to interact with matter and then deduce from that interaction. If we understand the medium that we're probing, if we understand what we're probing the matter with, if we understand the mathematics and properties of that, like light or electromagnetic radiation, which was very well characterized, by physics. Since we know light really well, can we probe matter with different types of electromagnetic radiation or light? Light's just kind of catch on. Most people just think of light as visible light that we can see, but there's a lot, ultraviolet, all that kind of stuff. We lump it all together as electromagnetic radiation, but commonly just call it light or EMR. If we understand that really well, can't we probe a sample of some element, maybe helium gas or something, and look at how it interacts with this electromagnetic radiation? If it does, which it obviously does, otherwise we wouldn't be talking about it. And by understanding the mathematics and nature of light and looking at the change that occurs after that light interacts with matter, we can deduce indirectly what's going on with the atom, looking at the energetics, electron. We're after electron structure, electron motion, energies of atoms, all that fun stuff. That's our goal. It's going to lead us into the realm of the whole development of quantum theory and quantum mechanics, right? Because, by the end of the 1800s, most physicists were pretty much, hey, we're done. Let's just apply our great knowledge to other fields like chemistry and biology. Ho, ho, ho. Oops, right? And then come the big names, Bohr and Einstein and all these crazy smart people that birthed, right, Planck. And we're going to talk about all these people that birthed the concept of quantum theory and quantum mechanics that revolutionized physics, right? Very late 1800s, early 1900s. So we're going to go through that story a little bit. I wish I could really go in. I could do a whole class just on that and the history of it. So we'll have to just summarize it in a little bit. But that's our goal with the structure, focus on electron motion, structure, and energetics of atoms. So let's review. Hopefully you already know quite a bit about light and its properties. So let's look at the wave properties of light. Quick little review of some light properties for you guys. Again, I'm assuming you've already studied this. If not, hey, welcome to the party. So we're going to look at electromagnetic radiation as a propagation of waves. That's the result of the transmission of energy, right? It's an energy. We're going to look at heat as a transmission of energy, light or electromagnetic radiation as a transmission of energy. And it propagates. So if you've got light, say, for example, propagating in the x-axis, it will have a propagation of electric and magnetic waves, right? So the blue ones I did as an electric vector and the green ones as a magnetic vector. Kind of hard to draw 3 dimensions on a 2-dimensional surface, but imagine if the light's propagating in the x direction, you've got an electric vector, let's say, moving in the z, right? And then the magnetic vector in the y, right? So Not that I can do this real well. So this is like an electric vector moving this way, and then the magnetic vector would be coming towards your face, right? That stuff. So you got these two separate waves going, woo, woo, woo. Chemists mostly just focus on the electric vector, right? Because we're going to be looking at its interaction with electrons, moving charged particles, which propagate off electric waves, right? Electric and magnetic waves. So we would think that electrons would interact with the electric vector. Hey, so what I'm going to do is we'll characterize light just by looking at the electric vector. We're going to ignore the magnetic vector for now, these transverse waves coming off of it. All right, so I'm going to redraw this with just the green electric vector, and then we'll look at how we can characterize this light wave. It's very similar to, like, I grew up on lakes in Minnesota, canoeing around, and you're canoeing away, and some speedboat goes by, and you're like, oh, you boogerhead, because then the waves start coming transversely. The boat's moving this way, and the waves go perpendicular from it, right? And some of them do it on purpose, you know what I mean? You'll be canoeing, and the speedboat will go by and then slow down because you get these bigger waves, bigger amplitudes. You're like, oh, and you're paddling away because you don't want those waves to hit the side of your canoe because you're like, whoa, whoa, right? Because up and down you go with the peaks or crests of these waves. You can feel the wave. You can see it coming at you. So you got to turn the canoe so you splice right into that wave. And then when it's done, you go and canoe back. And then the speedboat comes back around. You poopy head. Oh, and back into the wave. It's lake issues. All right, we're really going to characterize this 4 different ways. Here's that electric vector I was talking about. Probably the 2 most, I think, obvious or intuitive ways of looking at it. Like I said, when I'm canoeing away on that lake in Minnesota, I can see, yeah, that's a small, tiny wave. Maybe I don't need to turn my canoe into it. Oh man, that's a big one coming at me, like a lake tidal wave. Turn the canoe, because it's got a big height, right? Well, in physics and stuff, we call that amplitude. So if we draw this center line through, obviously the wave is up and down and up and down. So the height of that wave, or amplitude, would be, let's see, what color can we use? We'll use the same color as that. So if this is here, a peak or a crest, you could use a trough as well. It should be the same here and here. But we take that peak from the center line up to there. That is your amplitude. You could just as easily go from here down to the bottom of a trough. Easy one. And if you're a water skier or anything like that, you're familiar with waves and things, and you go, well, yeah, I know amplitude, height. Another one the one I probably use the most to characterize electromagnetic radiation is the wavelength. How far is it from peak to peak? Or you could go from trough to trough, doesn't really matter. So if I go from there to here, that distance is called the wavelength. Or the Greeks has the Greek symbol lambda. For amplitude, which is use capital A in my class. We're not going to use amplitude too much in my class. Wavelength, we'll use lambda. We're going to use that a lot. And again, that's the distance between peaks. So obviously the units would be some kind of length distance, whether it's meters or nanometers or angstroms, which is definitely not an SI unit. We're trying to get away from that one, but it's a pretty cool unit. Picometers, centimeters. So we'll try to stick with the metric units with some kind of metric prefix for meters. We're going to find out the wavelengths are radically different between regions of the electromagnetic spectrum, which we'll either talk in the end of this video, or maybe I'll make a completely separate video because I like to talk about each region and some fun little tidbits about each one. And I tend to ramble on a little bit, make it a long video. So this, I think, the 2 most obvious. Let's look at the 2 that are kind of less physically obvious, and I'll do that on the next board. This next one, frequency, for a lot of teachers and professors, this is their favorite way to characterize light. We'll find out later it's proportional to energy, that we tend to like to think of light in terms of energy regions, and we'll find out that frequency and energy are proportional, whereas wavelength and energy are inversely, so it's a little weird to think that way, but I just think wavelength is easier to think about. It's like this far apart, that far apart, that far apart, yada, yada, yada. But hopefully frequency makes sense to you. It's that Greek symbol nu. I always want to put a G in front of there. Isn't that an animal? So it's got that symbol. It's kind of like this weird italicized V. So frequency, if you think about it, imagine you're in a canoe and the speedboat goes by. And whether you turn your canoe or not doesn't really matter. But imagine you're going to have a stopwatch. And and you can see the wave, the water waves coming at you on the surface of the lake. Oh, here they come, here they come, here they come. Whoop, whoop. And you hit the stopwatch. Up you go, down you go. That's one cycle. Up you go, down you go. That's two cycles. So let's say we count a whole bunch, how many cycles go by in 1 minute or something, because they're moving pretty slow. Light moves a little bit faster. Right, so we could say that that particular wave from that boat was 15 cycles per minute, right? So it's a number of cycles, right? How many peaks pass a point in time? So if my canoe's here, how many times does that canoe go up and down? That would be one cycle from peak to peak, right? How long does that take? So it's a number of peaks that pass a specific point in time. How many times does the canoe sit on top, go down, up on top, go down? And we can do that as like cycles per minute. Whatever, it's just number of cycles per unit time, right? That'll be the units. So we tend to omit the cycles. That's just an implied thing. And when we're dealing with light, minutes would not be a good time unit because light's moving just a little bit faster than the water waves. So we use inverse seconds as the units for frequency when we're looking at electromagnetic radiation propagation, right? Or you could write, instead of 1/seconds, which is the best way to do it when you're doing unit line equations, so you can see the seconds is distinctly in the denominator. But another way to write that is seconds to the -1 power. That's easier to write if I'm trying to do it on Microsoft Word in one line, right? And that's given the infamous name of Hertz, right? H-Z, but most chemists don't use Hertz. We like to use the inverse time or inverse seconds for frequency. So if you think about it, right, we've got a distance between these peaks and a number of peaks passing a point per second. Can you see how this relates to the propagation rate? If you took the units of distance over the units of time, isn't that speed or velocity? Oh, can you anticipate what the fourth way to characterize light is on the next board? Last but not least, the speed of the light, or velocity, if you like that. So obviously distance traveled per unit time. So it's going to have units of length or distance over unit time. So obviously with light moving so fast, time probably good for seconds. And we'll use some SI units of meters there. Obviously, we could put any distance unit there if you want to put miles, or you could do miles per hour or something. It'd be interesting because we tend to think it more in terms of miles per hour. But moving in a vacuum, light's boogieing pretty fast here. 2.997925 times 10 to the 8th meters per second. So in 1 second, it moves roughly 3 times 10 to the 8th meters. Ooh, oh yes, they call it the streak. Woo, boogity, boogity. Right, that is a moving fast, okay? But it's not infinite, okay? But it's moving pretty fast. And we can alter the units if we want to, but that's what we'll be using. I will provide you this in my class. You don't have to memorize it. It actually goes out to more. It's not exact for what I'm giving you. It actually goes out more digits than this. A lot of people, like in introductory chemistry, I just say 3.00 times 10 to the 8th, which gives us 3 significant figures, which is usually pretty good. But this will give us 1, 2, 3, 4, 5, 6, 7 significant digits. More than enough where it's never going to limit us, but we can't treat it as an exact number because there are actually more digits. I truncated it off there. Now, that's in a vacuum, so technically it does slow down when it enters a different medium, like water or air or something like that. But as chemists, we're not going to be shooting light waves through water or anything. Maybe in a physics class, it'd be fun to see the light bend or refract or something. When I would sit on the end of the dock in Minnesota, my legs would be like this, and then they'd go, wah, wah. Right when they hit the water, the light slowed down. It looks like my legs would broken and bent. It's kind of fun as a kid. You're like, woo, physics is interesting. But for this class, we're just going to make the assumption that the speed of light's constant, right? Whether it's moving through air or a vacuum or something like that. Just to simplify it, all right? So hopefully you can put these two together and go, well, if it's distance over time, well, isn't wavelength the units of distance? and isn't frequency units of inverse time or inverse seconds. So if we took the wavelength times the frequency, wouldn't that give you units of distance over time? Oh, I see an equation coming. Yay! This is a formula you're going to use quite often, my friends. Hopefully you can see, right? If you take a wavelength, the units of distance, times the frequency, units of inverse time, you get distance over time, which is speed, the rate of speed, right? So speed of light, which we're treating as a constant, is the wavelength times the frequency, which means if the wavelength goes up, the frequency must go down to keep C constant. So they are inversely proportional. Remember that qualitatively so. Would that make sense, though? If I have a wavelength of this and it's propagating, right? You're gonna and I have a certain point, I'm measuring how many peaks pass per second. If the wavelength's this, you'll get some frequency, right? But if I decrease the wavelength, you're going to get more peaks passing per second, right? The shorter the wavelength, the more peaks or cycles pass a particular point per second. So smaller wavelength, higher frequency. Longer wavelength, fewer peaks pass per second, smaller frequency, right on? So remember inversely proportional, but we're going to apply a lot of math because we want to be able to interconvert between wavelength, because some chemists like to think of light in terms of wavelength, like myself, and others like to think in terms of frequency, and they're characterized different regions of light. Like I'm going to do some infrared light here. I like to think of that. I like to break up the different kinds of electromagnetic radiation into wavelength regions. Some people like to do that in frequency regions. That's okay. It's not right or wrong. It's just personal preference. Right? So here's a typical type of problem. Obviously, if this is a constant that I provide you, if I give you wavelength, you can solve for frequency. If I give you frequency, you can solve for wavelength. It's pretty simple mathematically, but you must be quite adept at using scientific notation or exponential notation. So know where your button is. Is it an EXP button? Right? That's my favorite one. This one doesn't. I have to go second function. There's a little double blue EE right there. So to get my 10 to that, I have to go second function EE. I like the ones that just have like an EXP. Boom. You just go bloop, right? But don't go times 10 to, don't do that. Use the EXP or EE button on your calculator. So if a form of infrared radiation, in the next video I'll talk about the different regions. It's one of my absolute favorite lectures. I could go for hours and hours and hours and days on it. So it's hard to clip it, but it's kind of fun for me. So if a form of infrared radiation, we'll talk about what infrared radiation is, but if you like your TV with your remote, bloop, bloop, you can't see it, but that might be shooting out infrared radiation. Some people think of it as heat waves, infrared scopes. We'll talk. I get too excited. I want to go to the next video. So let's say it has a wavelength of 8.7 micrometers, or in the old days, microns, right? So the wavelength is a millionth of that's about a millimeter. So, yep, that's pretty tiny. I don't even know if I can get a micrometer there. Ooh, maybe pull out one of your hairs. I don't know if you can see that hair there. See that gray hair? That might be in the micrometer range. So it has a wavelength, a wavelength of 8.7 micrometers. What would its frequency be? Okay, well, let's set this up and pop it in the calculator. So let's isolate our variable. We're trying to solve for what? The frequency? So would you agree the frequency would be the speed of light divided by the wavelength? Divide both sides by wavelength. So please isolate your variable for me. So let's plug in the speed of light. What was that? 2.997925? So 2.997925 times 10 to the 8th meters per second, right? So I want to get that seconds in the denominator. Meters in the numerator, seconds in the denominator. Set it up as a unit line equation. Now to divide by something, if it just has a singular unit, go 1 over that. Right? So we can go 1 over 8.7 micrometers or microns. And hopefully you can see you need to convert your wavelength units into meters in order for it to cancel out. We'll see that very commonly. We're going to deal with visible light a lot in the nanometer range. But this is the micrometer range. So hopefully you've got your metric prefixes memorized. So we want to go micrometers on top, meters on the bottom. Now, meter's bigger than a micrometer, so I like to put a 1 in front of the bigger one, and micro would be 1 times 10 to the 6th. And so that allows us to cancel meters on top, meters on bottom, micrometers on bottom, micrometers on top, leaving us with 1 over seconds or inverse seconds, and that's units of frequency, like cycles per second. We just do inverse seconds. We got a truckload of significant digits in our speed of light. We've only got 2 in our wavelength, and this is an exact metric. Things are exact. So this will go to 2 significant figures. So if you're going to pop this out, so type in your 2.997925. So there's my 2.997925 times 10 to the second function EE. What do we got? 8th. So that's the speed of light. All right. And if you have the EXP button, do that. Divided by 8.7 equals, and then I'm going to times that by 1 times 10 to the 6th. All right. So I get 3.45, blah, 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 3.445, blah, 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 lots of digits, times 10 to the 13th. So to 2 sig figs, that looks like a 3.445 vertical dash line between the 4s times 10 to the 13th inverse seconds. Right? That's a big number. Frequencies are big numbers. That's another reason I like wavelengths, because frequencies are so huge. So that's not going to round up. It stays as 3.4. So let's go 3.4 times 10 to the 13th. Now you can go over seconds, or you can go inverse seconds like this. So if I'm doing dimensional analysis, I like to have the seconds in the denominator like that. If I'm just writing an answer, a lot of times I'll just go seconds to the -1 power. I don't care. It works out fine either way. But that's how you can interconvert. I'm not going to do it the other direction, right? I could have started and given you this frequency and have you solve for that wavelength in some kind of metric units, whether it's centimeters or micrometers and whatnot. So in the next video, let's go through the different regions of the electromagnetic spectrum. I'm going to break them up into with how they interact. I want to talk about how they interact with matter and put them in regions that kind of interact with matter in similar ways, which is based on, we're going to introduce energy later, but they'll go into certain wavelength regions or frequency regions, and we'll have some fun with it.